Hello friends, today in this lecture of electromagnetic induction I am going to discuss one of the important topic, induction and energy transfer. So this is one of the crucial major point in this chapter. Also this point contains lot of weightage in terms of competitive exams like JEE, NEET, CET, and in board also you will find many number of numerical answer questions on this particular topic. So be careful while listening this lecture and focus on the content. Now listen here. In this induction and energy transfer, basically what is the theme of this particular heading, that is induction and energy transfer. Induction, it means actually it relates with magnetic field. Clear? So due to magnetic field, how electricity generated, how electrical energy is can be utilized, that energy generated due to some mechanical energy. So induction word is related with magnetic field, because as this chapter is electromagnetic induction. So basically magnetic field is present, that has been provided to you already, it is defined in the particular heading only. Magnetic field is present. After the presence of magnetic field and whenever the movement of the some conductor is taking place in the magnetic field, what actually electrical effects or what electrical effects are observed, or how that electrical energy is obtained, that we have to discuss in this particular subtopic. Clear? So this is the background of this subtopic. Now listen here. Actually this is a magnetic field, these dots indicates magnetic field, and that magnetic field is coming out of the paper, or it is coming out of the plane like this. In this magnetic field there is one loop called as ABCD, loop is present in this particular magnetic field. Then initial position, suppose this is B, then this is B dash and C dash. So initial loop is present only this particular area, in this area A, B dash, C dash, D. This is the initial position of the loop inside the magnetic field, and that magnetic field is uniform magnetic field. Clear? Okay. Now the length of the particular side AB dash, because there are four segments AB dash, B dash, C dash, C dash D and AD. These are the four segments made up of conductor. That four segments form a loop which is A, B dash, C dash, D, which is initially present inside the uniform magnetic field. So the length of that particular AB dash segment is X, then its width is AD is D, that is the width of AD is L. Clear? And after, what we can say, after certain instant of time, what happens? I have applied some mechanical force on this segment B dash C dash, and I try to pull that segment B dash C dash towards the right side, or I am applying force like this. So this segment is moves like this. As this segment is moving, what happens? Now initial position of the segment B dash C dash is now shifted to BC, and it is now termed as BC segment instead of B dash C dash. So this particular area, and which is indicated by this shaded portion, is now out of the magnetic field. So again important point is this dotted in this diagram, this dotted lines indicates the region in which that magnetic field is confined, or it is concentrated in that particular region only. Clear? Okay. Now listen here. What happens when the loop is moving out of this magnetic field with constant velocity v towards right side? Definitely what happens there, the magnetic field which is stationary, that magnetic field is cut by this particular segment B dash C dash. So definitely now flux links with that loop is changes. initially entire flux is present, so it from all the side of the loop are facing same amount of flux. There is no change in flux, so that the EMF induced is 0. Now I try to do some modification in the position of the segment, so that that loop is now started to move towards right side, so that there is a change in the magnetic field associated with that segment loop, so that as per Faraday's law we get some induced EMF. Clear? So this is a basic theme. Actually I am applying the external force, it means I am doing mechanical work. Since I am doing mechanical work in some specific time, it means what amount of power I am wasting, that I am going to calculate. Clear? So this is a mechanical power which I am going to utilize, but actually it is appeared as the electrical power. That electrical power we have to determine, because we are studying the chapter electromagnetic induction. We want electrical effects. Clear? Okay. Now when this particular segment B dash C dash is moved towards the right side with constant velocity c, so definitely I have already explained the magnetic field is change, and that change in magnetic field is experienced by that particular segment or conductor B dash C dash, and it now moves towards BC, so that that particular conductor experiences EMF across its terminals, and that induced EMF is given by E. Okay. So this is a simplified diagram of this particular structure, or that is extended diagram, in which this resistance R is a load. It may be anything, it may be bulb or any load, or it is a general load. So this load gets the EMF. Across this load we are getting this EMF, and this load possesses some resistance, due to which current starts flowing through the loop and that bulb will glow. It means what? Whatever you have did, what we have did, we have pulled that loop. It means we apply force. It means some mechanical work is done. That mechanical work is stored and it is utilized as a electrical work and electrical energy, so that that bulb starts glowing. It means using mechanical energy we are converting it into electrical energy. Clear? So how much power we have utilized, that we have to calculate. What is the force we have applied, that we have to calculate. Clear? What EMF has been induced across its terminals, that we have to calculate. What is the current flowing through this resistance, that we have to calculate. So what four expressions we have to derive? Induced EMF, induced current, force and power. Clear? That four expressions we are going to derive in this lecture. Clear? Okay. Now listen here. Now I am straightforward, I am explaining the derivation part. Listen here. What happens whenever you pull this B dash C dash segment towards right side? Now the new position of the segment is BC, due to which there is a change in the flux associated with that segment, and EMF is induced across this particular segment BC. Now as you know, using right hand palm rule, this magnetic field is coming out of the plane, so it is magnetic field is like this, and is, or if you consider right hand palm rule, this is for Fleming's right hand rule, VBI. I am using right hand palm rule. In right hand palm rule, this particular, if you take your right hand palm, in which if this particular fingers, okay, now listen here, if this particular finger, this is a moment of the rod, this is a moment of the rod, if this finger indicates what? This thumb indicates moment of the rod, right side, then this fingers indicates what? Magnetic field which is out of the board. Then this palm indicates what? Charge accumulated. So due to which charges are accumulated, positive charge is accumulated in this particular segment and negative is this. So current will flow like this. That's why current direction is like this. Current is downward. Okay, because this condition, thumb pointing towards me, it means I am pulling that segment here towards me. Then this thumb fingers indicates field out of this dotted, and this palm indicates current which is downward side. This current is downward side, so that's why current direction is downward. So it is an easy way to mark the direction of current. There is no necessity to mug up the things. Clear? Okay. So when we pull the segment, EMF is induced. Due to that induced EMF, this is a closed loop, so current is induced, and due to that induced current, now these four segments AB, BC, CD, AD are acts as a current carrying conductors, that is CCC, current carrying conductors. Clear? Okay. Now these four segments, okay, these particular four segments are placed in a uniform magnetic field B, and they also carries current. Initially segments does not carry current, they are only present in magnetic field. As now I have applied some constant velocity to them or force to them, so that they move with constant velocity. Now EMF is induced and current is induced, and they are still present in magnetic field. That's why this is called as current carrying conductors. Now as the current carrying conductors are present in uniform magnetic field, they experiences a force as per the Fleming's left hand rule. And what is the magnitude of that force? F is equal to I L B. So this is a force experienced by these particular conductors. Clear? Now listen here. If you indicates, listen here now. In this particular context, if you consider what you are observing what current is flowing in this direction. Listen here now. Current is flowing, if you take your left hand now, Fleming's left hand rule, because we have to determine the force. So current is flowing towards right side. So FBI in Fleming's left hand rule, thumb indicate force. This is magnetic field, forefinger, middle finger current. This is current. Then FBI, it means what? FB. B is what? B is outward now. Na? Listen here now. B is outward. Why? Because your this finger outward. Current is like this, and that's why force is upwards. That's why this particular conductor AB experiences force upward. This particular conductor experiences a force downward. This particular conductor experiences a force left side, because like this field, current, force. That's why force experienced by this conductor is leftward, it is upward, it is downward. And this is out of the magnetic field, so this does not experiences any force. So these two forces F2 and F3 are of equal magnitude. What is the magnitude? Bx. Why? Because length is now x. So bx, this is F is equal to F2 is equal to bx. BIL, length is x. Clear? And this experiences a force of Bill. Okay, actually it is Bill sine theta, but theta is the angle between length of conductor and your length. Theta is the angle between field, magnetic field, and your length of conductor. So as they have conductors, this particular conductor and magnetic field are perpendicular, because conductor is like this, field is like this, mutually perpendicular. That's why angle is 90. So sine 91. That's why it experiences Bill, and this experiences Bix. This is Bix, X, B, and L, and current I. Clear? As these two forces cancel out, only unbalanced force is F1, which is Bill. Clear? And this conductor does not experience any force, because it is out of the magnetic field. Because magnetic field is 0, force is 0. Okay? Yes. So to apply the Fleming left hand rule, what is the condition? Conductor should be in a magnetic field and it carry steady current. Okay? Yes. So this is actually explanation. Already I have explained you, but I am explaining you. Consider a loop ABCD moving with constant velocity V in constant magnetic field. This is the first point. Second point, a current is induced in clockwise direction. Loop segments experiences a force F1, F2, F3. To pull the loop with constant velocity V towards right, we have to apply some external force, and that external force should overcome the magnetic field. Clear? So that force which we have applied, that force is actually what? Work upon. That force is nothing but what? Force is equal to mass into acceleration. But here we have to calculate what? Power. Clear? So power means what actually? Power is equal to work upon time. Rate of doing work, it is called as power. And power work is equal to what? Force into displacement. Now listen here. This is important step. Work is 4 into displacement. Which displacement? We have displaced through this distance small dx. It is x. I have displaced from here to here. I pull it with a distance of dx with the with what force? F. That's why it is f into dx in time dt. That's why it is f into dx upon dt. So rate of doing work is called power, and that for f into dx by dt. Well, dx by dt is what actually? Velocity v. That's why I am getting what? Power is equal to f bar into v bar. Force is a vector quantity, velocity vector, so that's why we are getting power as a scalar quantity. That's why power is equal to f bar dot v r bar. Clear? Clear? So this is the expression for power P. Basic formula for power we have derived. But one important point to be noted here, this is a power we want in terms of electrical. We want to determine the power in terms of B, in terms of V, in terms of L, in terms of R, because this is electromagnetic induction. So we have to utilize the quantities which are present in this diagram. But to proceed further, you should write the basic formula for power, that is F bar dot V bar. Now I am going to discuss the derivations related to induced EMF, induced current, force and power, because as I already discussed, basic our aim is to determine the derivation or to derive the derivations. Okay, now listen here. As we discussed, this loop is moving with velocity v towards right side, so definitely what happens, there is a change in the magnetic flux. So as flux changes, definitely area change, as flux changes, there will be induced EMF. Clear? And now listen here. This particular diagram represent what? Extended form of this diagram, in which we are modeled this particular rod or this BC segment as a source of EMF BLV, and which is connected across the collective resistance R. Okay? Okay. Now as loop is moved towards the right, okay, as loop is moved towards the right, it means as this loop is moved towards the right, so what happens? The area which lie inside the loop decreases. What is the reason behind that? Because as I apply the force on this segment and I move it, definitely what happens, the x decreases. This x distance covered by this loop now inside the magnetic field decreases. So definitely distance decreases, so area lying the loop decreases, so magnetic flux inside the loop decreases. It means in the paper you have to write, as loop is moved towards right side, x decreases, A decreases, phi decreases, E induced. Clear? Okay. Due to decrease in the flux, current is induced inside the loop. Clear? Because as the flux decreases, there is EMF is induced, and due to induced EMF, current is produced inside the loop. The induced current, now one important point, I discuss it. As current is induced, now that segments act as a current carrying conductors, which are placed inside the magnetic field, due to which the force is experienced by that particular conductors or segments. So that induced current gives rise to force, and that force acts in opposite direction to the applied mechanical force. If I am pulling it towards right, that force acts towards left. Clear? Okay. So this is the basic theoretical statements that we have to write while doing the derivations. Okay. Now I am going towards the expressions, derivation point. Magnetic flux through the loop is given by what? What is the formula for magnetic flux? BA cos theta, where theta is the angle between area vector and magnetic field. In this case, area vector and magnetic field both are perpendicular, because area vector in this case, area vector and magnetic field both are parallel to each other. Okay, not perpendicular, because in this case field is outward and area vector is outward, both are parallel to each other. So the angle between them is what? 0. Cos 0 is 1. That's why flux is equal to only BA, which is equal to A is what? L into X. What is the area swept by the loop when it is moved? L into X. L into X. It is a area of the loop. Clear? Okay. So this is what phi is equal to BLX. Now this is actually important point, so I have put it inside the box. As x decreases, phi decreases. Means what? Initially this dotted line, this loop was initially here. So this side was here. That's why the entire distance x lies within the magnetic field. It means this entire segment lie inside the magnetic field. But as I moved this segment BC towards right, this area is out of the magnetic field. So now what it is out of the magnetic field means what? Magnetic flux decreases. So as x decreases, magnetic flux decreases. Clear? Okay. Now flux decreases, it means definitely there is change in the flux. So as there is change in the flux, as per the Faraday's law, EMF is induced, because whenever there is a change in the flux associated with any loop or any system of conductors, there is EMF is induced in that conductors. So that EMF is given by mod of d phi by dt, because now we are not dealing with sign, we want only magnitude. That's why E is modulus of d phi by dt or mod of d phi by dt. Now d by dt, what is phi? Actually phi is BLX from this equation. This is equation number 1. So from this equation it is BLX. So I have substituted BLX. So E is B constant, length of the conductor is constant, that is segment. B is constant, uniform magnetic field. So it is dx by dt, because now try to correlate dx by dt coming here. Okay, it is coming by the way of mathematical approach, but from concept point of view, if you think, then also you can easily determine. As x is changing, x is changing with respect to time. Whenever I am pulling the loop outside, as time progresses, the area, the part of the loop inside the magnetic field decreases. It means what? That resultant active length of conductor which is inside the magnetic field is now decreasing. It means it is changing. It means what? That x is changing by factor dx when time changes by dt. That's why this is what? Dx by dt. Now dx by dt means what? Actually velocity. That's why this E is equal to BLV. Okay, that's why we already discussed. It is that loop is moving towards right side with constant velocity of V. That V is dx by dt. And for that V, who is responsible? Change in distance x dx and change in time dt. That's why this E is equal to BLV. This is an important formula. What is E? E is equal to BLV. E is equal to BLV. Clear? And where actually this is a maximum induced EMF. Actually it is BLV sin theta that we have discussed, where the theta is the angle between magnetic field and velocity. In this case magnetic field outward, velocity right side, both are perpendicular. That's why sin 90 is 1. That's why E is equal to BLV. Clear? So first calculate flux, BA, area, Lx. So BLx is the flux. Differentiate it, d phi by dt, which is equal to E, which is equal to BL dx by dt, and dx by dt is V. That's why E is equal to BLV. It is an induced EMF. That's why I have drawn this diagram, in which now this conductor is replaced with BLV. Clear? Okay. Another important, that's why this conductor is replaced with BLV and this is R. Now one important point, why these two conductor does not experience any force. Okay, there is a one important reason here, because this conductor is not perpendicular to the field. Okay, so that's why these two conductor does not experience, there is a induced EMF inside that particular two conductors. Clear? Okay. Now listen here. Now this induced EMF is BLV, and these four segments form a closed circuit, closed loop. So definitely there will be flow of current, induced current, and that induced current is induced EMF upon resistance. What is induced EMF? BLV. So I is modulus of E by R, which is BLV by R. Important. Induced current is BLV by R. Induced EMF is BLV. Okay. Now particular these three segment current carrying segments experiences force. Which three segments? Segment AD, segment AB dash, and segment this particular DC dash. This segment does not experiences force, because electrical force, because it is outside the magnetic field. We are applying external force on this particular side BC. It is not electrical force. Clear? Okay. Now listen here. From the diagram, these forces, this F2 and F3, these are equal and opposite, because this segment experiences for upward, this experiences downward by Fleming's left hand rule, that is FBI. FBI. There's in this case thumb indicate force, B field, this is actually field and current, FBI. B is outward, in that case your B is outward, in this is current, thumb indicates force. So in this case force is upward, in this case force is downward, because current is like this. Clear? So these two equal forces and directions are opposite, that's why they cancel out. And what is the magnitude of that two forces? Bix. Clear? So resultant force, that resultant force only acts on which segment? Segment AD. And that force, that is F bar, is F1 minus F1 bar, because this force is like this, whatever I am applying, and this is leftward. That's why I am a minus sign here, which is modulus of F1, which is ILB sin 90. Why 90 here? Because that in case of Fleming left hand rule, whenever a current carrying conductor, this is now current carrying conductor, that current carrying conductor is placed in uniform magnetic field B, so it experiences a force of ILB sin theta, and theta is the angle between length and magnetic field. In this case magnetic field is outward, length is vertical, so the angle between them is 90 degrees. That's why it experiences a maximum force, which is ILB, as sin theta is 1, because theta is 90. Clear? Okay, that's why this F is equal to ILB. Now we know that induced current is what? BLV by R. I substituted here, so it is BLV by R into LB, which is actually what? B square L square V by R. This is actually what? Force experienced by the conductor. F is equal to ILB sin theta. It is a generalized force whenever a current carrying conductor placed in magnetic field. Now what we required? We required a force in terms of BLV, which is what? B square L square V by R. So we derived three formulas. First, what we derived? Induced EMF BLV. Second, induced current I is BLV by R. Third, force. What is that force? B square L square V by R. Clear? Okay. Now last, power. Power is actually what? I already discussed you. Rate of doing work upon time. That is force into velocity. What is the force we have derived? B square L square V by R. I substituted here B square L square V by R. So it is power is equal to B square L square V by R into V, which is B square L square V square upon R square. Clear? B square L square V square upon R square. So in this way we derived four formulas. First, induced EMF. Second, induced current. Third, force. And fourth, power. All these are electrical quantity, in terms of electrical quantities. So when we actually, what is the conclusion from this, or what is the gist of this particular topic? That is, when I apply the force on this segment and pull it towards right side with constant velocity V, that time I am doing mechanical work, because I am mechanical energy is applied. That mechanical energy is utilized, but that mechanical energy is never wasted. It is converted as a electrical energy. Clear? And that electrical energy is appeared as a heat, and which is equal to what? This B square L square V by R. So if you connect the bulb here, in that case what will happen? If you pull this segment, that bulb will glow as you pull the rod. If you stop the pulling, bulb will not glow. It will off, because there is no EMF is induced. What is the reason? Because motion has been stopped. So this is the motional EMF concept. Clear? So once again I am revising. What are the formulas? Induced EMF BLV, induced current BLV by R, then force is equal to B square L square V by R, and power is B square L square V square by R. Clear? So in this particular context we discuss the important topic, that is induction and energy transfer. And this particular power is appear as a heat. Whatever mechanical energy we are applying, mechanical force we are applying, that mechanical force is converted into heat, and it appears as a heat in terms of electrical energy. So if you try to calculate power in terms of electricity, what is power? I square R. So power is equal to, listen here, power is equal to what? I square R. But I is what? What is I? BLV by R. I am substituting here. So it is BLV by R whole square into R If you calculate this, you are getting what? B square L square V square upon R. Same formula, no? Listen here, B square L square V square by R, B square L square V square by R. Clear? So that's why when you pull the conductor towards right, then definitely what happens? You are using mechanical energy, that is appeared as a what? Electrical energy in the form of heat, and that electrical energy or electrical power is actually what? I square R. Clear? So in this way the mechanical power is converted into electrical power, and that's why this is called as induction and energy transfer. I think now you are clear why this is called energy transfer, because you have provided a mechanical energy and it is stored as a electrical energy. It means that energy has been transferred from one domain to another domain. That's why this is called as induction and energy transfer. With the help of magnetic field, you can convert mechanical energy into electrical energy. And what is the formula for that power that you have derived? B square L square V square by R. Clear? Okay. So in this lecture, we have discussed thoroughly the important topic induction and energy transfer, in which we derived 4 formulas, that is induced EMF, induced current, then force and power in terms of magnetic field B, length of the conductor L, resistance of the loop R, and motion of the conductor with velocity V. Thank you.